Yesterday, you heard a lot about spatially resolved and spatial frequency domain reflectance as a means to do physiological monitoring. And you even saw a device in action and played around with some of the software tools to get some intuition. Today, we're going to march down to the time continuum and focus on time resolved in temporal frequency domain. We'll have the first talk focusing mostly on instrumentation and applications, and then I'll bore you with the math afterwards. So it's my pleasure to introduce Thomas Sullivan, who's professor of electrical engineering at Notre Dame. Tom did his undergraduate degree at Northwestern, if I remember correctly, and doctoral work in electrical engineering at Stanford, where he started working in kind of the optics realm, looking at implantable fluorescence sensors. He then came here and worked with Bruce Tromberg and really innovated new ways or improved instrument designs for a frequency domain of photon migration in a variety of biomedical contexts, and then started his faculty life as an independent investigator at Notre Dame. You started there in 2013? 16. Okay, sorry. 2016. He is also technically an alumnus of the earlier version of the short course. So of course I'll take credit for all of his brilliance. And and so let's welcome Professor Sullivan. And of course, in the future, he'll just be known as the advisor of, and Sashi is going to do even greater things.
Yeah, so Anna and Shashi are going to keep me on my toes. Hopefully I don't bore them too much because they've seen all these slides before in some version or another. But you can add the color commentary, be like, yeah, that didn't really work. You know? So good morning, everybody. Great to see you. I sat down yesterday evening with a couple of my good friends, David Kachia, Rolf Sager, and Mihaela Balu, and all said you were a fantastic group. So my expectations are really high. I like interactive discussions. I want to teach you what you want to learn. I don't want to teach you something you don't want to learn. I haven't turned on the screen yet. Just making sure. Yeah, I can do that. Okay. You should be good now. Yeah. So we're going to talk about diffuse optics, diffuse optical spectroscopy, or near infrared spectroscopy. We still haven't decided what we want to call ourselves. We've got really good colleagues who use one acronym and we use a different one. We get together. That's actually a point I'll touch on, is standardization in this field. It's really an area that needs development. So what do you know about diffuse optical spectroscopy? I saw some of your bios and some of you do some of that. Those of you who do that, would you mind sharing what it is so I kind of know where we're starting, where we are? So Andreas's group, a couple reps here. Yep.
So as to
front row, perfect. Yeah.
I do more software optimization right now.
Okay. Yep. Okay. CW, frequency domain, doesn't matter.
So I did CW in the past, now we're focusing on
okay.
Cool. We do CW for multiple sources architecture layers.
Okay.
For the crowd, okay. It's a variable patch. We're using it for detection.
Okay.
And monitoring control, and we do.
Have you talked to Shashi about wearable?
Yes. Yes.
Perfect. Others? Yeah.
Yeah, we have a live as it purchase, rates are around.
Yeah,
so you can pretty much measure the light travels around then get.
Exactly. That process, diffusive, both mathematical terms, right? Because diffusion equation, and use that to model like propagation, but also just broadly speaking, you think of something diffusing and spreading out. That is both our strength and our weakness, right? It's our strength because we can get photons deep into tissue, interact with lots of different molecules, and hopefully measure something about those molecules, whether it's absorption and scattering. I'm assuming at this point you've talked about absorption and scattering. You understand the transport. But, you know, on the other side, right, when you do that, you lose spatial information, right? Because this is a macroscopic imaging or sensing technique. But that's what we need, right? If you want to get to the brain, you know, that's 15 millimeters plus, you know, below the skull. That's where you want to be. If you want to get to that breast tumor, right, that's a centimeter or two below the surface, you can't help but, you know, lose spatial resolution. But that's okay, right? That's where we fit in. I know some of you do OCT, right, and other type of microscopies. So we kind of know where we all fit together in this realm of biophotonics. So let me disclose first that I'm going to talk about some work toward the end of the talk about a company I co-founded called Nearwave. I'm inherently conflicted because I co-founded that company, but I thought you might be interested in learning about what we're doing. And this is a great segue. Sorry, what was your name? Second?
Sorry, Ezekiel.
Ezekiel. So this is what you were talking about, right? Yeah. Has everyone done this experiment? Put a flashlight or a torch on your hand and look at the light that happens when it comes through it. Really quickly, not a trick question. What do you see? Put on your scientific observation lab coat and tell me, what are the observations you see in this experiment? We started with a flashlight, white light. Yeah, we lost all the other colors, right? So, I mean, I'm sure this is a review. You know, hemoglobin is very strongly absorbing in the visible spectrum. It's least absorbing in the red, and that's where we operate, in the red to near infrared. What else do you see in this picture? What's that? Veins, yeah. Another hint that there's something about blood that's really important here. And that is really where NIRS, I mean, really is. It's a lot about blood oxygenation monitoring, hemoglobin monitoring, because we have really strong absorption there. We have really strong contrast. Good. So you had SFDI yesterday, right? So my students are going to roll their eyes because I don't know how many times they've seen my foot, but they're going to see it one more time. This is my foot. I'm showing you this picture of my foot because I broke it. That's why I got an X-ray for it. And I love to ask if anyone can identify where in my foot it's broken. Yeah. 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 So I agree that looks like there's something wrong with that. It's most likely arthritis, actually. It's not the broken bone part. But there's definitely some pathology there. Over here somewhere? Yeah, nope, this is all good. I think you're actually seeing some scattering too. X-ray scatter too. Yeah, which one? So we count them 1, 2, 3, 4, 5. One? Nope.
I'm saying it's more like
Down here? Oh yeah. Yeah, you've got a lot of these. No, that's all normal joints right there. You're getting closer though.
It's not.
I don't give trick questions. Great. That's the crack that's not supposed to be. You see it, you can see kind of like in 3D, this like circumferential crack. Yeah. I did that. I was at a meeting not unlike this, where I was talking to a student. We were walking to lunch and I rolled my foot off the edge of the sidewalk and the rest of me came down on top of it. And I limped my way home back through the airport and into the doctor's office, where they told me that if you're going to break your foot, that's not a bad way to do it. So all you got to do is wear a boot for 4 to 6 weeks. If I had broken it about a centimeter up, I'd be looking at surgery and a screw to put that back in. I show this because, you know, this is what most people are thinking of when we think of medical imaging, right? But when you do diffuse optics, we think more like this. So I don't know if I did it before or after I went to the doctor. It might have been before I went to the doctor. I went to the lab and I asked one of my PhD students, who now works for the FDA, was former alumna of this course as well, to measure me with SFDI, which you saw yesterday, right? So this is with a Modulum research grade system, right? And you can see the information we get. It's a lot different than the information we see at the hospital. Now, what's going on here, right? We see a lot of hemoglobin-like contrast. You know, this is the oxyhemoglobin channel, but I can tell you when I looked at my foot, it wasn't oxyhemoglobin. It's basically a bruise, right? It's other states of hemoglobin, but that's where the algorithm puts it because there's really strong, you know, red absorption right there. So what is diffuse optical spectroscopy? If I could put a general term to it, a class of methods for measuring deep tissue, I'll say greater than 1 millimeter or so, optical properties, absorption, scattering, also fluorescence. There's a bit of that. We don't do that, but you can. Typically non-invasively, also minimally invasively. You could do this with endoscopic probes or injectable sensors and things like that. Oftentimes with, you know, red to near infrared light. As you know at this point, you know, we're sensitive to hemoglobin, oxy and deoxyhemoglobin. And then what we like to look at in our lab, particularly in the context of breast cancer, is water and fat as well as a marker of tissue composition. I'm going to start with CW before we get to the quantitative frequency domain and time domain, because that's this essentially to a doctor, that's what the state of the art is. Right? We have to realize that, right? That when you're going to work in a hospital, you're going to work with anesthesiologist or a trauma surgeon. When you tell them that you work in NIRS, you know, this is what they're going to think of, right? They're going to think of the CW tissue oximeters that are out there. So that's where I would like to start. Now, kind of jumping to the conclusion here, we'll revisit this, but you know, every single FDA cleared device that uses diffuse optical spectroscopy is continuous wave imaging, okay? And as we will see, right, these devices can't inherently, or at least easily, separate the effects of absorption and scattering. You certainly can't do that if you only have a single source detector separation, because you're taking one measurement of light attenuation, and there's no way mathematically to separate why that light got attenuated. Was it due to absorption or scattering? But we have all these devices. We have FNIRS, functional near-infrared spectroscopy devices. We have pulse oximeters. We do have CW tissue oximeters. That can be okay. So in a pulse oximeter, we're measuring the oxygenation of blood in the arteries, okay? And the reason this works is because arteries pulse and veins don't, for the most part. So that pulsating artery gives you a signal you can lock onto. So in other words, if you're measuring light transmission through the finger and it's going up and down, it's a really good assumption that that light is going up and down because of the arterial component of the blood, right? And that's why pulse oximeters are sensitive to the arterial component and not the venous component. Okay? So, you know, if you're going to measure changes in oxygenation, you're going to need two wavelengths. You know, typically in pulse oximeters, you're on either side of the isospecific point here, typically around 660 nanometers and 940 to 980 nanometers. Of course, you have a choice of wavelengths. Would you choose a different wavelength? Or just think about that. What would, knowing what you know now so far in the course, if you were to design a pulse oximeter, what might be some of the disadvantages of using 660 and 940? So a short one and a long.
You're essentially missing out a lot of overlap between the 720 to 850, where both peaks are distinct. So,
Okay.
Yeah, close to 700, you have the oxygen and around 850, you have oxygen peaking.
Yeah.
You're just missing out
You're
that.
saying if you had more spectral information, you'd do a better job separating. Yes. And that's true. So CW, brain cerebral oximeters typically use 4 wavelengths, right? They've got one, you know, right around 7 to 6. Good. What else?
The 950, right?
Yeah, it's like 940 to 90.
Yeah, yeah, water peaks over, hemoglobin is just you can say.
Yeah, where you get some attenuation there. Yep. Thanks. What about path length, penetration depth, scattering? What's different about those two wavelengths? Yeah, right. Yeah, so you've got potentially a partial volume effect, right? Each wavelength is interrogating a different volume. Now, when you do it in transmission, maybe that's less of a concern, but certainly in reflectance, that would be a pretty big concern. You know, that could be an issue, for example, pulse oximetry. One of the exciting things that whole field started was to try to measure the oxygenation of a fetus, right? So looking through the mother into the baby, trying to ascertain, right, how healthy was that fetus. And you imagine using those two wavelengths, that's kind of a big issue, right? Because, if you've got a very shallow penetration depth, a lot of scattering, a lot of absorption of these lower wavelengths, one wavelength might be not even be making it to where you want it to go. So this is other, issue in diffuse optics we have to be aware of. Oftentimes we sweep it under the rug, but it's something that, it could be a good thing in that you can use the fact that different wavelengths penetrate at different depths as a way of getting depth-dependent information, right? Particularly if you're doing some sort of multi-layer recovery or something like that, it's something you need to consider in your models. Oftentimes, we use homogeneous models. We kind of ignore that because we assume the tissue is all the same, but that of course is going to introduce some bias right into those measurements. Good. So here, this is a great textbook, by the way. I don't get any money or any points on Amazon if you buy it, but Irving Vigio and Sergio Fantini, wrote this fantastic textbook about this almost 10 years ago now. Really great for if you want to study diffuse optics. I mean, they say it's quantitative biomedical optics, so it's got a chapter on OCT and acoustic imaging, but really it's a diffuse optics book. There's like 6 chapters on it. And in that textbook, you'll find this figure and you'll find this equation about how you extract that pulsatile arterial blood oxygenation. And, doing this equation, we have extinction coefficients, which are all constants. And then we have change in the absorption coefficient, right? And this is where that issue of scattering comes in, because we don't measure with this device the change in the absorption coefficient. What do we measure? Scattering. Not even scattering. What's the thing we measure? Yeah, attenuation, change in amplitude. Right? We're measuring this. And in that, right, it's going to have a scattering contribution and absorption contribution. So if you were to do this from first principles, you would need to know what the scattering is and apply what's called the differential path length factor to do that. I literally just last week had to train my materials colleague who was making some new flexible detector. Supposedly did pulse oximetry with it, and they want to put me as a co-author on the paper, and they got a number that made sense. And I said, "But how did you calibrate it?" I go, we need to talk. Which maybe I should lead to a list of main points. But one of my main points in diffuse optics is it's really easy to get a number that makes sense. That doesn't make it right. So, once you go through something as students and you've solved this hard problem, or you've done this, reconstruction and everything looks good and you're getting numbers that make sense, you're getting 8% oxygenation, you're great, job done, I'm going to move on, publish the paper. No, the next step is you try to break it, right? You try to perturb it in ways that lead to outcomes that are expected. And when they don't lead to an outcome that's expected, and Anna knows this, then it tells you need to go back and figure out, where was the assumption, for something as simple as a bug in your code, sometimes actually. Okay, so pulse oximeters work moderately well. COVID taught us that we had some issues with skin pigmentation bias. Folks with darker skin were seeing oxygenation readings that were artificially higher than they really were. And the reason for that is essentially the way pulse oximeter manufacturers work is they oftentimes don't come up with a differential path length factor. What they do is they just measure a bunch of people and they have a reference measurement, which oftentimes is just another pulse oximeter. And they essentially do an empirical fit to make the data measured with their device fit the other one, right? You know, that can work if you have a good representation of the population, right? If you have a good representation of the pathology of the population, right? If you've got someone who perhaps has some sort of disorder related to blood flow, you know, for example, that they're not going to be represented. It's only going to work in a particular range that you calibrate. So doctors know this, or doctors should know this, that, you know, the pulse oximeter is really a binary measure. It's either good or it's bad, right? The difference between 92% and 93% is meaningless, right? Which is why we all got nervous when people could buy pulse oximeters on Amazon during COVID, right? And monitor themselves at home, because they didn't understand that there's no difference between 92% and 93%. But there's a big difference between 85% and 99%, right? But you understand that, right? Because you're tissue optics people. But the instrumentation is relatively simple. I won't dwell on this, but you can buy chips from Texas Instruments and other manufacturers that have LED drivers built into them. This is just one example, this AFE 4490. It'll drive 2 LEDs. I mean, this is the measurement sequence. It measures, does a dark measurement, one LED on, another dark measurement, another LED on, over and over and over again. All you have to do is connect your photodiode to it, and it makes a really good class project. It's relatively inexpensive, and you can take this data and process it and do your own measurements. Any questions? Has anyone built a pulse oximeter in a class, lab? No? Well, I know you guys did. You did? Yep. Yeah. It's really easy way to get, you know, real meaningful data and manipulate it. First thing we do is measure pulse rate. I always get a kick out of someone's like, why is my pulse rate 45? It's like, well, let's see. Let's look at your data. Nope, that's just you. So then I mentioned there's, you know, a number of CW cerebral and somatic or body oxygenation measurement devices out here. Here are 2 of the more used disseminated ones. The InVos system, which is now owned by Medtronic. Non-in system, which is used. And what I like about these systems is, you know, particularly this system, it uses 2 sources and 2 detectors with overlapping volumes. So basically get 2 channels of measurement. And it does a decently good job of isolating superficial, you know, contributions to the measurement, which is a longstanding problem in our field, right? From, you know, deeper tissue oxygenation measurements. But really, at the end of the day, these are still just change monitors, right? We're not quantifying. I mean, you can attempt to quantify oxyhemoglobin and deoxyhemoglobin, but you're going to have some assumptions built into that, have some sort of empirical model built into that. You know, in some cases, you know, in some different modes, you have to enter the skin pigmentation, right, to try to correct for those effects. But they can do, in some cases, pretty neat things. This is an older study now, but this is using the InVos oximeter here and measuring a group of patients who are going in for cardiac surgery. So this is not during surgery. So actually, and I just learned this in preparation, it is a group has recommended that these type of brain oximeters should be used intraoperatively during cardiac surgery, right? So if you're going to start to mess with the heart and the perfusion of the brain, having a direct measurement of that seems like a good idea. We'll come back to that in a second. But in this study, this was a little different. This was measuring brain oxygenation before they went into surgery, okay? And the type of cardiac surgery varied, right? You know, could have been bypass or, you know, or whatever, but it was not controlled for in this study. And what they looked at was their baseline oxygenation. So just looked at 2 groups. So basically measured them for some period of time. Looked at the minimum oxygenation over that range, that time range. Separated it between above 50% and below 50%. That's a pretty gross kind of separation, right? Now below 50%, you think someone would be dead because normal, you know, brain oxygenation is about 70 to 80%, but they were alive. But essentially what this data showed is regardless of how successful the surgery was, regardless of whatever the surgery was, just that metric alone was a predictor of how many of those patients were going to be alive a year later. You're familiar with these survival curves? It's the fraction of people who have survived after some period of time. And if you look at the total population, just by looking at that pre-operative cerebral oxygenation, you could pretty well predict who's going to be alive a year later, which is pretty incredible when you think about it. What do you think is going on? What should the clinician take away from this?
What the it was 30 days before the surgery, they are doing a reading. Then
Just right,
1 year
right
after
before
the
the
surgery,
surgery.
like 1 year after surgery.
Yeah. Yeah, but they're seeing how many people have, no, they're just doing the reading once,
Okay,
just before the surgery.
okay.
Then they're seeing how many people are alive up
After,
to a year later.
but they're not monitoring the patient.
Nope. Just one reading. That's a great question. They're adults. That's all I know. Adults going to cardiac surgery.
Is it, so the question is what physicians can take away from this?
Well, why is there a difference between these groups?
Maybe after the brain surgery, the,
No brain surgery. Cardiac surgery.
oh, sorry, cardiac.
Yeah.
After the cardiac surgery, there is a drop in cerebral perfusion.
There's no measurement after surgery. Measurement is just before surgery.
I think I missed it, but what is SC?
So this is that measurement they took of cerebral oxygenation before the surgery. And if it dropped below 50% sometime during that measurement period before the surgery, this was their survival. If it never dropped below 50%.
Something to the fact that if somebody surgery at 5 has a kind of like a marker to say, okay, this is a good time to work on surgery, or hey, there might be something else to investigate that before I go right.
Yeah, right. So there's something already happened that in some sense dictated their fate, right? That regardless of the success of the cardiac procedure, essentially there was already some. Right? So,
addition, baselines went up, right? Further compromised. So maybe aesthetic, if there are differences.
Yeah.
So anesthesia. And
right.
so maybe.
Right. And actually, a really, really important thing is you're saying that is maybe this is the population you want to have that brain accelerator on during the surgery. Maybe you don't need it for these ones. They're going to be fine. But it'd be really bad if these descend, even more worse. Yeah. It was not controlled for. Yeah. Yeah, it was like 1,200 patients in this cohort, I think. Yeah.
Go with statistics, I'd say put all the patients equivalent in the oxygen rich environment.
Yeah, I can't speak to that as a clinician. I don't know how well that's going to work. Really interesting. So, I mean, one way this technology could potentially be used also opens up a bunch of ethical questions, right? Like, would you not do the surgery on those, right? Or I think more likely you would do the surgery in all different kinds of cardiac surgeries. Yep. Yeah, so this one, I didn't get this slide. So this is a subset of this population, except we looked at a group of patients, the authors looked at a group of patients that had other cardiovascular risk factors or comorbidities that basically, meant that surgery is not going to go well for those people. So when you combine that information, right, the difference is even more distinct. And not only that, they passed pretty early.
What is it like there's like a AC.
Oh, yeah, so basically, well, I mean, when you look at survival curves, you can get information like this. Like, I usually look at these in terms of cancer survival because that's the research I do. But here, what this is saying is that if someone makes it past the first 2 months, they're going to be fine. Right? We see that a lot with kind of cancer and mortality curves, right? If you have an aggressive cancer, if you make it past a year, for example, right, they tend to be fine.
So most people during most people for today's before the cardiac surgery would probably be on medication. Is it the case that the population that's at risk maybe are on multiple medications?
They do. I mean, that wasn't controlled for.
Right.
Yeah. So I mean, this is compelling. So this is one, potential use of this technology. Absolutely. Yeah. So that kind of leads to, I wanted to try to give a summary of how these oximeters are used clinically. And as I already mentioned, it is some professional groups have recommended that it's being used during cardiac surgery. So, it is, not all ICUs have this equipment across the United States, but a good number of them do now. Other types of surgeries, orthopedic, et cetera, more kind of research-based, not regularly used. In intensive care, particularly for neonates and pediatrics, it's standard care in many of the NICUs across the United States now. For adults outside of the intraoperative setting, again, it's still kind of mostly used for research. And the reason is, there's a company that's created these devices to identify focal hemorrhages. Basically, you're just looking for regions of the brain where there's high absorption. But the reason, I mean, these have been around for, 20 plus years now. There's still quite a bit of conflicting and certain evidence that shows that using these devices actually improves patient outcome. So there's plenty of studies like this that show things that kind of make sense, right? That you can look at differences between cohorts. But when you actually put this in a random, controlled clinical trial setting, the study looks something like this. So you get patients who come in, for example, due to a trauma or intensive care unit, and you put the oximeter on, all of them, and then you randomize them to the doctor can see one reading from one patient, and they can't see the reading from the other patient. And when you look at these studies, you see some endpoints that are like, well, if you know the oxygenation, can you do a better job of it responding to desaturation in the brain? And of course, if you have the oximeter on there, right, you can do that better, right? Because you get a very quick response, right, compared to other measures that you might have, and you can do that. But at the end of the day, does that actually improve patient outcome? Or in some cases, a couple papers that looked at brain injury, and it's very conflicting information. Some studies say yes, it is helpful. Other ones said no, there was no difference. The patient would have done just the same, statistically speaking, had the doctor not had this information. So, why do you think that's the case? Do you have an idea? Yep. Right. Yeah. Well, why is there conflicting studies? Why aren't the studies agreeing? Right. Yep. Yep. Yeah. Right. Right. Yep. Yeah. I agree. So kind of the clinical variables. Now let's say those were well controlled for, right? And we still saw this variation. I mean, you're absolutely right? And that goes into this. But I think we still see, even when it is pretty well controlled, we still see studies that don't agree and there's uncertainties.
They don't really know how to use that. So you get a lot of information, but how do you actually translate it into effective?
Yeah. So you get this new piece of information. What do you do with it?
Yeah.
Yeah.
things. Maybe get the test, show it,
Yep.
right? But we are kind of analyzing things such as house, like all kinds of stuff that
It's a non-specific measurement. Yes. This is my new thing. I think that I say this every time I go up and speak is that's a problem our field needs to work on. Is we make non-specific measurements of physiology. Right? We measure blood, water. You should have some combination of all three of those things in your body, right? So how do you have the controls where the information you're looking at is valid for what? Yeah. What else? Yep.
So
Yeah.
even I wear a lot of extra 20, 30 kilos of weight.
Yeah.
Just started.
So I think you're getting at something more than just kind of what the patient is thinking, but
Yes.
lack of standardization in how these measurements are taken, right? Where you take them, how long you take them, what condition the patient has to be in when you take them. Yeah.
And the conservative. During the time, you don't know how the patient think about it.
Yeah. Actually,
Brings you looking at a blood chemistry panel, very well specified bounds.
Yep.
These are probably most clinicians probably like to have an absolute cutoff when they either intervene or don't intervene, and the baseline is very.
Right.
There's no-
Yeah. So that's it. I mean, there's, you talk about standardization and how they're used, but there's also standardization in how the technology is, right? What are the source detector separations? What is the underlying algorithm that is correcting for skin pigmentation or correcting for superficial effects? And those algorithms vary from instrument to instrument to instrument. And we notice there's papers on this, right? You can find these papers. The folks out of Europe and Switzerland love to publish these papers where they take, 4 different oximeters and put it on the same person and they get 4 different readings of 4 different trends. Yeah.
So those are devices, just fixed source of
Mhm.
things. Independent of the patient then, right? Even.
They might have a, pediatric one and an adult one and that's it. Yeah.
Yeah, exactly.
Right. Right.
No way you're gonna do this.
Right.
Much of the design of these sites.
Yeah. Right. That's really kind of the physiology is different, right? And we're creating a non-specific macroscopic measurement on people who are not one the same, right? So does everyone see where I'm pushing towards it now? Right? Quantitative measurements, right? We need to have measurement modalities that are rooted in physical principles, physics, math, that we understand. We understand the physiology, we understand the structure. And I say this not talk about machine learning, right? We're in an era where it's really exciting to just take a bunch of data and throw it to train a model to look at this. And there's a risk in doing that because you're sweeping all these things under the rug. And if we're going to have problems now with the ways these devices are used, imagine how it's going to be used if you have no idea what they're trained on and what kind of population is trained on and what does that mean? I mean, personally, what I think all that's going to do is reduce the sensitivity of the measurement because you're going to average all these effects together, which I'll say at the end of the day, machine learning is just a polynomial curve thing, right? Which is many, many dimensions of many variables. So that's where, where I'm motivated, where groups of us are motivated to try to make more quantitative measurements, to take data that's more rooted in physical models, multi-layer models, tomography models. And, some areas, I think FNIRS, is now become probably the most successful, at least commercial area of near-infrared spectroscopy. Shashi's working on a review paper, and we didn't think we were going to write an F-NIRS paper, but it's kind of turned into an F-NIRS paper because that's where all the commercial development is. And it makes sense because you can use CW techniques for this if you're just looking at localizing where the contrast is. If you don't really care as much of what the contrast is, but if you're more worried about where it is, where it's localized, where it is over time, you're doing temporal correlations. CW makes a lot of sense, right? Because it's really sensitive, right? You can use really sensitive detectors. You don't have problems of bandwidth like you would with frequency domain and time domain. And you can do really nice things like they do at Washington University, take these high density measurements and show resolution that's pretty close to fMRI, which is pretty incredible, when you think about it. You take $1,000 device and get something that looks very close to a $3 million, right? And that's why there's been a lot of kind of interest and excitement in doing F-NIRS, both topography or 3D construction tomography, which I'm not going to talk about today. We could do a whole lecture on diffuse optical tomography. So much so that I put one of these plots in here because I was curious about it. I just came across this AI-driven journal searching paper website. You've seen it. I just used it because it made this plot automatically. I didn't have to export the data or anything. But you can see there continues to be exponential growth. 1,000 F-NIRS papers last year. And of course, this includes applications. Most of it's actually applications now written by neuroscientists. But of course, a large amount of technology development is still ongoing as well. Okay, so the other thing, right, that contributes to that variability, more specifically, is the idea of scattering. Scattering is different. Differential path length factors are different, right? Just like the pulse oximeter has its calibration factor, these oximeters are going to have their own calibration factor, and that's going to vary from person to person. So you've played with Virtual Photonics Toolbox. We're going to play with it again this afternoon. And I just love showing this because if I took a CW measurement, I just measured reflectance, and I used a single source detector separation and plotting what that expected reflectance is for different pairs of optical properties, doesn't get any more clear than this, is if you had a different set of optical properties, right? In one, this absorption is twice as high as this, but the scattering is half of it, right? If you measure at this source detector separation, you're going to get the same reflectance, right? Doesn't get any more obvious. You cannot separate the effects of absorptions. So what else could you do? You could do multiple source vector separations, which is what those devices use. Typically, a very limited number of source vector separations, like 2. But even then, right, it becomes an issue of sensitivity. Can you really, if you had 2 measurements, separate those 2 curves with a great deal of fidelity? Right? It just depends on how much noise is in your system and how much variability there is. And is this a really good model in the first place, right? Is the diffusion homogeneous semi-infinite model the right one for what you're doing? So Shashi said, right, it's possible, right, if you're careful and you make a really good measurement. And that's going to lead us into other things. So just to summarize this first section here, continuous wave, its benefit is that it's low cost. Right, you could buy those chips from Texas Instrument and put together an oximeter, relatively straightforward. Cost you, $20, probably all in. High sensitivity, could be super miniaturizable. I didn't show this, but we have a project where we make injectable pulse oximeters. We fit in the needle and we can measure from inside a tumor. It's fast, and of course it's developed, it's commercialized. But we see a lot of variability, right? It's difficult to quantify optical properties with just a few source vector separation. You can distinguish different types of contrast. And then there's technical difficulties when you do multiple source detector separations, like you're assuming your coupling is the same at every single source detector, which practically is not true, right? And oftentimes there is no in the field, patient measurement calibration to correct for those effects. And honestly, I think the combination of those things is what's resulted in this uncertain evidence as to clinical effectiveness. That's putting it politely. There are some clinicians, anesthesiologists, that have just written off NIRS altogether because of this. Oh, we played with this 10 years ago and we didn't see any differences, therefore the whole field is hogwash. And we fight against that. So we have to write the grant application, because I know that person's going to be on the study section, I have to say, this is not your, grandfather's NIRS, your grandmother's NIRS, right? We're doing something new and different, and this is why. So what is that thing? We want to be quantitative, right? We want to be quantitative because it's easy to measure absorption in that test tube, but it's difficult to measure absorption in that test tube, right? Because we don't know what that path length factor is. When we apply the Beer-Lambert law, we need to plug in the length, right? We don't know what it is. In fact, it's not a single, right? This model is not good on its own for this equation, for this experimental setup right here. So what else can you do? If a single source detector pair with constant intensity is not enough information to measure both absorption and scattering, here's three things you could do. You could use space, right? So we saw that already with measuring multiple source detector separations. You saw that yesterday, spatial frequency domain, right? You're using the concept of space, in that case, the spatial frequency domain as opposed to the real spatial domain, to look at how photons travel different lengths. And as a result of that, they're going to be affected differently by scattering absorption. Well, so you kind of saw that already. I'll spend the rest of the time talking about using time, right? The idea that you can time the arrival of photons that come out of the tissue, right? So now you can use a single or maybe a few source detector separations, but by measuring the ones that arrived earlier, you'd expect them to be less affected by absorption because absorption lengths are longer, characteristic absorption lengths are longer. And your late arriving photons, right, would be more affected by absorption than scattering. Boston's going to be much more quantitative with this later this morning. And wavelength, right? You can use the other knowledge about the spectral dependence of both absorption and scattering, right? If we know our measurement data is made up of blood, water, and fat, we can use that extinction spectra as constraints in our fit. You could also use the scattering spectrum as a constraint in that fit. As you can see, this is me. This is a picture of me taken with blue light for 70 nanometers, where the absorption and scattering length is about the same. And then in the near infrared at 50 nanometer, where the absorption length is much longer than the same. I think you know why this is the case now, but I want to make sure you're awake. So why don't you tell me, why do these pictures look different? Right, so that's my question, is why does using different wavelengths make this picture different? Yeah, so we're seeing more scattering, or the effects of scattering here, because we've lost this contrast, right? All my freckles are gone, right? What does this also tell us about the freckles? Yeah, right. Melanin is a very strong visible light absorber, right? So these photons are either getting absorbed or they're reflecting back. There's one scattering event, so to speak, right? So this is really good for microscopy, right? We want few scattering events, right? We want all our photons that are not absorbed to be reflected, right? So we get a nice high resolution picture of all of my beautiful imperfections. But if you don't want that, you can use multiple scattering as a way of washing out that contrast, right? So not only do you have less absorption from melanin, but these photons are going much, much deeper in tissue and are affected, by absorbing that water. By the way, there's $1 billion industry that knows this. You know what that is? Yeah, cosmetics, right? And I don't oftentimes wear makeup. But my understanding is there's a foundation you put on first that smooths out your complexion. All that foundation is a multiple scattering. All right. So yeah. My kids have dried milk on their face, you know, it's not quite the same effect. So if you're doing diffuse reflectance spectroscopy or hyperspectral imaging, you're oftentimes using many wavelengths, using this spectral dependence in your models as a way of separating absorption and scattering. And that's one way of doing CW technique, but introducing more information in order to separate those effects. All right, so why would you want to switch to quantitative diffuse optical spectroscopy? You know, the benefit of taking absolute measurements is, you know, the ability to make more valid comparisons between different types of subjects. You could potentially use this to correct other techniques like fluorescence, do quantitative fluorescence imaging, or try to approach quantitative photoacoustic imaging or flow imaging if you do spectroscopy or speckle imaging. If you separate absorption and scattering, you have different types of contrast, right? So you might get extra contrast from scattering that could give you some more information about the biology that you didn't have when you just lumped it all together as attenuation. And that all leads to, you know, quantitatively and computationally higher spatial accuracy. You can, you know, make a single measurement, for example, like in the time domain, and by measuring photons that come out at different times, get that spatial information in a single measurement. Right, that's one of the neat things about time domain imaging. But there's a cost to that, right? These techniques are, you know, more complex, more bulky, typically, oftentimes require calibration, et cetera. And, you know, if I could summarize what my lab does is we try to reduce these costs, reduce disparities, techniques more accessible. Because we want to do this, right? We want to measure breast tumors which have scattering, which is nothing like the surrounding tissue around it. So if we want to get a quantitative, or as quantitative as we can get, given the limitations of the models, measurement of that tumor concentration, then we better take into account those effects of scattering. Otherwise, we're going to see things. And when you do that, you can, you know, compare populations in a quantitative manner. See that in younger premenopausal women with breasts that have higher mammographic density on average, right? You can see that higher optical absorption, higher water absorption, you know, compared to older postmenopausal women where there's less water, there's more, relatively speaking, you know, fat absorption. So how do we do this? We'll do time domain first. So, what time do I go into? Yeah. Okay. Okay. So we're doing good. I think I'll. So in the time domain, we send in a narrow pulse of light, sub-nanosecond pulse of light into the tissue. I should come over here because I'm ignoring the side of the classroom. Problem is I have to look this way. I'll be on this. So sub-nanosecond pulse, we inject into the tissue, and we looked at the shape of that pulse after it's remitted, oftentimes in reflectance, but in transmission as well. So we'll see this afternoon when we do the lab, the computational lab. But if you had tissue that had higher absorption, you would see that effect more in the late arriving photons. Why is that? What's special about late arriving photons and absorption? Yes, all the photons travel at the same speed. So what does it mean if they arrive later? Longer path, right? Longer path length, more opportunity to absorb, right? Because absorption happens much less frequently in this regime than scattering. So we see that effect more so in the later arriving photons. And then if you kept absorption constant and changed scattering, right, we see that effect more in the early arriving photons, right? Because those are you know, going to be affected more by that change in scattering, that change in path length that happens early on. Now, to be clear, it's not one or the other, right? The whole curve is affected, which leads to, you know, kind of practically when you do model fitting of these curves, kind of choosing what time range you use is kind of a critical choice, right? Because you could be biasing your results one way or the other. Yeah. Yeah, I'll get there in a second. Yeah. the reason it's difficult, one of the, because it's difficult, another way you can do this is in the frequency domain. So we'll talk about this as well, where instead of sending in, picosecond or sub-nanosecond pulses, at, megahertz type frame rates, we use a CW source, but we modulate it, right? We turn it on and off really fast. And if you turn it on and off fast enough, which ends up being in the tens to hundreds of megahertz, and you measure the light that's emitted, what you can perceive is a phase delay between the measured light and your injected light. Right? And now you have a sense of time delay, essentially, but it comes in the form of frequency dependent phase. So we have two things we extract from this data. We, of course, see a change in amplitude, right? Because we don't collect all the light we inject. So that's going to be due to changes in both absorption and scattering. And then we see this phase delay, which, I think it's more straightforward to think about that as an effect of path length and scattering. But like all things, it's not that simple. And Boston's going to talk about this afternoon. Is you see the effects of both absorption and scattering in that phase delay as well. So if I create analogous plots and look at how amplitude and phase changes as a function of modulation frequency, we see as you increase absorption, right? It makes sense. We see a reduction in amplitude across the bandwidth here. But, relatively speaking, we actually see more of an effect at shorter frequencies, right? So there's something special about the zero frequency. What's that? You see, that's a CW measurement, right? No modulation is a CW measurement. And you can actually see, right? You get really good sensitivity to absorption. Right? So looking at phase here, you can see as you go to higher modulation frequencies, you see, there's a general shape of the curve, right? The phase delay increases with modulation frequency. And if this were a straight line, you can see it's a little bit of curve to it, but if it was a straight line, that would just be the fact that you have a shorter wave, right? If you have two waves and one moves this much, and you have a shorter wavelength one, and it moves the same amount in time, the accumulated phase is much higher, right? You've gone through, potentially different periods. So we see that general effect. So, phase delay always goes up with frequency, but where the information is actually encoded is in the curve from this. What is the dispersion of that phase relationship, right? You can see that curve changes as scattering changes. And again, it's not just one or the other. It's both absorption and scattering affects that. I'll pause for questions because this is actually a very complicated topic, and I kind of brushed the surface of it. Yeah. Yeah, it's okay.
Those information is actually seen. But there would be no face to it.
Right. So
How did you measure?
yeah, well, so I mean, if you just did this would be a CW measurement. So you'd have no way of separating absorption and scattering. Right? But if you go to 200 megahertz, and you can perceive both the change in amplitude and phase. Now, this is incredibly handy. You have two variables, right? Two measurements and 200 megahertz. Now it's a nonlinear problem, so it's more complicated. So, I mean, you're kind of getting to how do you make the measurement? I mean, we do it kind of the simple ways, which is just you sweep through these frequencies. Sure. You could construct a wave that has harmonics. You run into dynamic range issues because just like it was probably mentioned yesterday, that tissue is a low pass filter to spatial frequencies. It's also a low pass filter to temporal frequencies, right? And basically for the same reason, right? As you go to higher and higher frequencies, I gotta go to whiteboard. I don't have this term in my presentation, but I'll use it now. Photon density wave. And so what's happening when we, send these photons in, we're basically sending in waves, right? Like waves in the ocean, right? So, you might have a peak there, and then, there's a minimum, and then there's another peak, right? So if you did a snapshot in time, it might look like this. So just like if you threw a stone in the ocean and you watch the waves move away, that's like number of photons going through the tissue, Okay. Now, if you have a low frequency like this, these waves are going to retain their shape further into the tissue because scattering, the random movement of these photons within these waves, right? That's where it gets really confusing, is within these waves, you have photons that are scattering, right? And when you have a lower frequency, it's going to go deeper into the tissue before they blur out, right? And that contrast goes away, the differences between the peaks and the valleys. But if I have a really high frequency and my waves look something like this, right, they're not going to go very deep before they all blur together. I'm not sure if that exactly answered your question, but it got me on a point I wanted to make.
And then it's sort of.
Yeah. Other questions? Mhm. Yeah.
They have the pump.
Yep.
So. The spec side, then the speed is slower than the other. But they're faster than the other.
This one is before this one. Yeah. So is the speed of light changing in tissue?
Yes.
No.
Why-
Sure, yeah, because you know the speed of light can't change. Tissue speed of light is the speed of light, right? But what's happening is the most number of photons, right? The peak of that curve is arriving earlier than it is over here. So in other words, if you know, I drove from Long Beach this morning. I got in an Uber and we could take the carpool lane, right? I arrived a lot earlier than someone who was by themselves and got stuck in traffic, right? So these photons had a longer path length on average because of the increased scattering. So maybe if I sketch that out, be clearer. Can everyone see this over the computer? Right, so the difference between path length is you have these photons that are in and they're scattering a lot, you know, 10 times a millimeter potentially, right? Or a centimeter. No, millimeter. And you know, on average, if there's, you know, more scattering, right, you're going to have photons that do this and you have photons that do this, right? And when you have more scattering, you're going to have more photons that do this than do this, right? So these photons arrived earlier, right, because their path length was shorter, right? And these photons arrived later because their path length was longer. Okay. Is it clear now? Or? The source vector separation is constant. That's, yeah.
And speed. Speed measured different to different time.
Yeah.
Yeah.
Yeah, so you can, I mean, you can use this as a way of measuring depth, right?
Yes.
So, I mean, that I alluded to that. There's depth information encoded in that curve, right? Which, you know, goes back to what model are you using to fit this curve? Is it a depth resolved model? Mhm. Yep. Yeah, and the answer to the question is use time coordinated. So you get a really sensitive detector where basically you're timing with picosecond resolution. How many photons arrive at each time? Oh, so I mean, a photo, well, first they use photo multiplying tubes. Really high gain single photon converters. Now there's movement towards, it's called silicon photomultipliers. Yeah, it's small. It becomes an issue of gain because you're measuring maybe only a dozen photons.
That kind of thing that very good.
So you, I mean, you definitely need, yes, you need to have an avalanche photo detector or a photometric too. And I should point out, you're not just doing this at one laser pulse, or you're doing this at a 10 megahertz method and collecting data for 5 seconds. Right? And the reason you have to do that is because you build up this curve essentially statistically. Right? Every pulse, you might get a few, dozen photons or something, and you plot them where they are. And then you do that again and again and again, following the repetition rate. Yeah.
So, I think you were trying to explain it, but I just in a nutshell, increasing reduced scattering means that when you're going down, the scattering of smaller parts than much more. When it goes down, the increase in reduced scattering means that the blue one is the smaller reduced scattering.
No, more scattering. It's this, right? It's more scattering, yeah. Imagine those photons are rattling around more before they get out.
Okay, so the one with decent frequency is the one that's coming out scattering the least.
Look at the numbers of it.
Right.
Blue is the highest.
Right, and
So it's delayed in time. It's also reduced as well.
Increasing reduced scattering, it's like increasing reduced.
Yeah, right. Increasing, reduced. Just say more scattering. Yeah. That's correct. Yeah. You're good. It's the nomenclature. Good. We feel good now? Good. I mean, this is kind of where it's all at, is kind of on this slide right now. The rest is kind of details. Yep. For a frequency domain? So, I mean, it just depends on what laser they're using. It's usually, I don't do this regularly, but some kind of tens of megahertz. And obviously you want to be able to go faster if your laser will support that. Oftentimes if you want to make a small compact system, you're just using pulse laser. Okay. So have you seen this plot yesterday? Did Rolf show this? Different version of it? Yeah. Did David show it? Yeah. Yeah. It's from my page, but I knocked it off David's. This is really just showing that, I don't know how a pure mathematician would agree with this statement, but in the time domain and the frequency domain are Fourier transforms. So that's all that's showing. And you saw it with the spatial frequency domain and the real distance over here, where you can take multiple source vector separations, or you can do SFDI and do this with patterns of spatial frequencies, right? We're doing the analogous of that in the time domain, where we can either use the real time with a pulse, or we can look at the temporal frequency domain, the modulation frequencies. Okay, so I think we might have gone through a lot of these details already, but how do you do this practically? Well, this works because, the characteristic time to an absorption or scattering event is quite different, right? So as we saw, scattering events happen, photons only travel a fraction of a picosecond before they scatter, where, absorption takes half a nanosecond. Right? You can multiply, divide by the speed of light there, right? And get your characteristic distance as well. So as we talked about, pulse laser diodes, rates in the tens of megahertz. And you don't need a lot of optical power to do that with these really sensitive photodetectors. I mean, you could crank up the power, and people have transilluminated the brain. You can do that and safely get signal on the other side. And the reason is that you're using really sensitive single photon detectors and really sophisticated electronics, where you're timing the arrival of each of those photons, so you can build up these curves. One of the systems I think we still have here is the Hamamatsu TRS-20, which does that. More recently, there was kind of an exciting company out of California here called Kernel, developing a time domain wearable near system. But I think they ran into some financial trouble, so I'm not exactly sure what their status is right now. But actually really amazing engineering if you could get that to work, right? Take all that sophisticated high-speed electronics and get it to work in a chem. We're trying to get it to the frequency domain. The time domain's even harder. And one of the there's many not trivial things about doing that, not the least being, having sub-nanosecond lasers and time correlated single counting electronics and doing that in an electronic system that doesn't dissipate too much heat at the same time because that takes a lot of power. But also the fact that in the time domain, you're inherently sensitive to room light, right? You're using really sensitive detectors. You're just counting the number of photons that are arriving at each time, and those photons could be coming from anywhere, right? And you can very quickly saturate that detector. Is there anybody here that knows about the status of the kernel or works for them? I know people who've consulted with them. They still exist. Is anyone from a lab where they had one of their systems and was evaluating it? No? So maybe I should unmute the recording, but what I heard is that it actually didn't go so well. That the first few labs that used the device, did notice some kind of practical issues with it, which is not surprising at all, right? It's very difficult to do, and I don't think it's impossible, but it takes quite a bit of sophisticated engineering to do that. Now, do I think you could ever get this to work like while someone's riding a bike outside in the bright sun? And that's maybe not the application you should go for, but certainly for example, some applications even in a hospital or a clinic or in children where you want something that's low profile and less sensitive to motion artifact, this could be a really good thing to do. So there's been some improvements in just like you saw, miniaturization of time domain technologies. The group out of Juan and Plimi has kind of led in this, both in developing the devices, the detectors, the integrated circuits that do this time correlated single photon counting, to the point where they have a wearable system, sense that you could put it in a backpack and wear it. That was the case. We had wearable frequency domain systems 10 years ago. But the ability again to do that is pretty amazing. It's pretty incredible engineering. Now, because that requires really sophisticated electronics and engineering is, here I trained at BLI is Bruce Tromberg and colleagues, team and many others in the field, has looked at frequency domain as an alternate way of doing this. And there are, ISS is a company out of Illinois that creates frequency domain systems that you can buy. They're not FDA cleared. For whatever reason, they've decided not to pursue that. But groups such as mine and my colleagues at Boston University and at Medical School have taken these and both scaled the technology up to do tomography and also scaled it down into handheld devices. And this is what my lab has worked on with the company we spun out. And this is what Shashi is working on, something like this, and in collaboration with electrical engineering department here at UC Irvine in doing this on chips. So taking those electronics you need to generate the modulation and detect that amplitude phase and doing it in a integrated circuit that's 1 to 2 millimeters wide. And this is not unlike the maturation of ultrasound technology. It used to take a dedicated exam room, now be done with a device that has, at least last I heard here at UC Irvine, all the residents were given pocket ultrasound units. Is that still the case? Oh, they weren't even like rentals. They just like gave it to them. Oh, wow. Wow. Can I get some of those units on eBay? Which is probably not quite legal, right? Because it's a regulated medical device. Yeah, gotcha. I mean, to the point where there is a wearable ultrasound for doing a breast cancer screening. It's ISO No Health received FDA clearance not too long ago for wearable breast ultrasound. So I want to talk a little bit about what goes into a frequency domain system. So we need a laser. The reason we need a laser is not because it's coherent and not necessarily because it has a narrow line width, but it's because we can modulate it. You can only modulate off the shelf LEDs, up to maybe a few megahertz or tens of megahertz or something like that. I mean, more sophisticated purpose made ones, you can maybe get to tens of megahertz. But for a device that was made for telecommunications, we can easily modulate lasers up to gigahertz, which is much more neat to do these visuals. We need sensitive detectors, but not as sensitive as the time domain, right? Because we're not sending in packets of photons every nanosecond, only a dozen photons at a time, right? The light's on continuously. It's going on and off with the modulation, but we're sending in many more photons than you are in the time domain. So while we still need to use something like an avalanche photodiode, we don't necessarily need a photomultiplier tube that requires 1,000 volts of bias, right? And then you need a device that generates that modulation and can detect that modulation. And this is just a picture of a vector network analyzer, which is a piece of electronic equipment we can buy off the shelf that does this. It's used for characterizing circuits, but we're just hacking it to, instead of characterize a circuit, connect it to a light source and ensure the modulation. So you can assemble one of these systems for probably $2,000 now. Pretty decent system, given how low cost these items are now. And then you take this data and then you give it to Vasan for his next presentation, taking that amplitude and phase, fitting it to your model of light tissue interaction and extracting those optical properties, which we qualitatively saw. There's a few different ways of doing that. This is actually what we do, is we do a full fit where we take the quantitative amplitude and phase data over many frequencies. This is real data I'm showing you here. I know at some point the conversation of single versus multi-frequency is going to come up. I'm going to punt on that for now. We do multi-frequency fits here, and we calibrate the system so all these numbers are quantitative, and we do a full fit, the solution to your model of choice, whether it's transport. You don't have to do that. In fact, the ISS system that you buy doesn't do that. It does what's called the slope approach, which is you have multiple source detector separations, maybe 3 or 4 source detector separations. Instead of using multiple frequencies, you use a single frequency typically, although you can choose what that frequency is. And you look at the slope of the phase, and then you linearize the amplitude. So you take the log of it, scale it by the source detector separation, and you linearize the amplitude as well, and you look at the slope of those two curves. And when you do that, you actually get a really nice equation that you can plug this into and get a decent estimate of absorption and scattering. Yeah.
Distance.
Right. Yeah, exactly. Yeah. This is for a single frequency. Yep. Okay. Yeah. Yep. If you're interested in how well each one works, we did a conference proceeding on this a couple of years ago. And you can see, there are regions where, you need to have a long enough source detector separation for this to work, essentially. But with modern computational tools, it's just as easy to do this now. I put this back in kind of the 80s and 90s when you needed graph paper and you needed to fit the line. That made a lot of sense, but now you can just plug this into MATLAB or Python.
Even if yes, I mean, it sounds like this is just a multi-distance measurement. Why does this do better?
You've got the face. That you still don't have in CW multi-distance. You don't have things. Gives you that face.
So with their data, do we get to
Yeah.
Why is it there?
Yeah. Why do you think? Your signal to noise ratio is going down. And ultimately, typically the reason is because our detector has bandwidth, so it's less sensitive. You see the same thing in the phase. Right? That actually is a great question. That has to do with calibration. So when we do these measurements, I don't have a slide on calibration, but essentially, when you build one of these systems, you want to measure how your tissue is affecting the amplitude of this. That's not the only thing in your system affecting it. Your system itself is, right? Your detector has a bandwidth association. Your laser has a bandwidth association. There's a phase delay in the electronics, in the delay that goes through your fibers that go to your tissue. So you have to calibrate that all out. And that calibration is susceptible to that same signal to noise ratio issues. So basically what's happened is we're getting a really poor calibration. And what we're seeing is some of the effects or the ringing that the system is contributing. So this is, I mean, these are kind of two different things. I'm illustrating the full frequency foot fitting approach here. Ignore that. This is the other approach where you use a single frequency. You measure the phase, right? The slope of the phase is a function of distance. So that's what rho is. That's the discrete dependent variable there. And the slope of the linearized amplitude. And when you have those slopes, which is S sub phi here and S sub EC, you can plug this into this nice closed form equation approximation and get out mu A. So that's really easy and fast to do. Here, what you have to do is a nonlinear. So you either have to have a lookup table that has all this in there and finding the closest answer essentially, or you're doing some sort of iterative nonlinear solve, which is more computationally intensive than just fitting a line.
Advantage of the system. So this is the line that
Yes, you have to have multiple. So if you're interested in, so you can't use this, for example, to do depth distribution. The data all has to
okay.
No, this is not trivial stuff. Took me a while before I felt I understood it. Yeah, right.
But it would seem that the signal to noise ratio seems to be less. 500. Does that mean the majority of the experimentation you wanted to have?
You want to include the highest SNR data you can.
So when you developed this, your intention was to showcase at what point are we to start to see like such erroneous outcomes that we would want to stay outside of that.
Yeah. Again, it's coded that up. Basically, you go to yeah.
We did.
Right. When you fit this data, I mean, we can do this automated, we can do this kind of subjective, but basically you pick an ending wavelength range. Because if you keep including more, you're just gonna
Yeah.
Now the question is, well, what frequency do you use? So the answer is it depends on the application. It depends what you're interested in. So, for example, if you had tissue that had a relatively high absorption, you might not get a lot. So in that case, doing multiple frequencies might not be worth it, because your detector sensitivity is always going to drop with frequency. So you might as well use the lowest frequency that you can if you've got really absorbent tissue.
Let's have a specific and you want so when you're doing design, this is the wavelength range I want to optimize. This is just, or is it reverse?
Yeah. I wish the design process was that linear, but sometimes not. But generally speaking, we're interested in breast image, which generally is relatively low absorption and high scattering. So you do get a lot of information. Other questions? Mhm. You need to go to higher frequencies to see that dispersion essentially. Yeah. Right, which oftentimes our equipment can't get to. But you need a gigahertz or something. Right. Okay, so some technology. What have been some advances? Miniature laser diodes. There's a laser diode technology called VCSEL, vertical cavity surface emitting laser, that's really small. Those are chips that are like 500 micron by 500 micron. You can do really dense integration of multiple colors or put it in an implant. Detector technology followed similar to time domain, where we started with photomultiplier tubes and then moved to APDs, and our lab is really pushing the use of silicon photomultiplier detectors. Modulation, right? You need to generate these frequencies. You can do that with a crystal if you're doing single frequency, and you're doing this pure sine wave or modulation, or electronically using something called a phase lock loop, or you could use a direct digital function generator essentially to create these frequencies as well. Oftentimes, when we do these measurements, you can do direct sampling of that high frequency wave, at the hundreds of megahertz. That does tend to take a lot of power to do that. So it's oftentimes advantageous to mix it with another frequency that down converts it to a lower frequency that you can measure more easy with your electronics. And then if you did it well, you've got amplitude and phase, but that's not what you want. What you want is absorption and scattering. So you need to have some sort of model, which is on the version, lookup table. Or there's been a lot of efforts now to train, deep learning, machine learning models to do this. On the technology side, I just want to mention that this is really the state of the art, is trying to push this into chips. Right, to be able to do this, we don't have to buy the $2,000 analyzer, but you could buy a chip for $10 that generates the modulation, detects the modulation, basically just like that Texas Instruments chip I started with at the beginning of the talk. That's the vision. You connect your light source, connect your detector to it. Now you have a tissue imaging system. And I'm sure Shashi would be love to talk to you more about that, since that's what he is working on. Yep. So, in recent years, it's been exciting working in this field in the past 8 to 10 years. My colleagues at Boston University have really pioneered going fast with this technology. Group looking at how do you do novel combinations of sources and detectors in order to optimize where you're getting the contrast from in the tissue. This is a really exciting area. And even doing tomography. There's been a few papers now at Washington University in Birmingham that have shown that when you introduce this phase component, you get deeper sensitivity. Not only deeper, but also more uniform. Right? So you're not as essentially, typically you're in these techniques, you're very weighted in sensitivity right under your source and detector, which makes sense, right? Because all the photons have to go through those points in the tissue. But when you measure phase, it turns out that averages out a little more. You get a little more uniform depth sampling. So here's what we've done is, we're trying to make this frequency domain instrumentation more accessible, more easy to access, more portable. And this is what the company I co-founded here was working on. There's multi-frequency frequency domain optical spectroscopy. 6 lasers in it. There's 3 detectors in it, so there's 3 source detector separation. And does this all, at kilohertz rates. So the idea is like an ultrasound, you can take this thing and spin it around, and that data is streamed to your Apple device of choice, and does all the model fitting inside of it. And I'll show you the video here, of this thing in action. We've got a phantom here. You can see in the middle, there's an inclusion underneath meant to simulate tumor. And you can see this is completely wireless. This is plotting amplitude with wavelengths. And you can see, right, that reduction in amplitude is just giving that inclusion on the phantom in real time. So we want to make this easy to use, right? When we were doing some early studies with the system, it was taking an hour and a half to do a single exam. And the idea here is that we can do this in 5 minutes. Right? What's that? So, well, you're asking how it affects the optical practice, right? So, I've got a separate thing that kind of looks at the difference between what it comes down to is you take this data and you extrapolate what is the blood concentration in the body. And again, this is what research is so you can, if you're measuring a phantom, you can take that data and quantify absorption and scattering. You can spend more time talking about why these curves look different, even though the shape of the contrast is exactly the same. I don't have time for that though. We can talk about it later. But then you can take the data, interpolate it, and I'll show you one more video here. So maybe we'll do a couple slides and then take a break since we're right at 10 o'clock. But this is a little more of a raw video. But this kind of shows you from the time you turn on the device, it's that iPad, the software there, you start measuring. In this version of the software, you can see it's actually interpolating the data in real time. And the reason it can do that is because in the front end of this thing is a position sensor that's watching the probe moving on the front. In this version, it's basically an optical mouse sensor. The same thing with moving mouse on the wrist. Yep. Yep. Yeah, that's exactly what we're doing. From an operator reproducibility. I mean, it's not hard to measure over the tumor and the image that has important information in it, but it's hard to do that repeatedly with different people. Because we've introduced a problem that complicates our quantitative this is the ability to have the humans do it, at will. So the studies, which at this time we had not really developed in some stuff, but we would basically literally draw points on the graphs and just measure every single point. And you could go back and draw that grid every single time and really using the same exact area. So this device, that we can't that's there's 3 detectors, so it's measuring multiple sorts of different. I don't have the slide in here, but we actually have done tomography. So the idea to get some depth information. At the end of the day, that might look, you can kind of see, this is the operator variability, where the probe stands across. But the idea is to interpolate that and then simply build a 2-dimensional image. And it goes fast as well, right? So if you don't want to do imaging, you just want to look at quantitative photoplasmography, you can do that. We can quantify changes in oxygen and global concentration, or get it to the concentration quantitatively, right? You do that fast enough to pick up these really nice features that you see in these waveforms. This is an application area which we're not pursuing too much right now, but I think is kind of exciting for potential areas of critical care, for example. I think we should take a break. I don't know if you want me to finish or not. Kind of what I've done. The last part is a bit about it. You were wrong. They're still getting their butterflies, yeah. Okay.